Okay, so thanks a lot for the invitation. This is a joint work with David Helm and Xiao Liang. Okay, so what I'm going to speak about is a result on the Tate cycles on certain unitary Shimura varieties. This is an explicit example of general philosophy. That, so if you have a x even dimensional Shimura variety over finite field, say FQ, then the philosophy is on this Shimura variety we expect that the supersingular locus contributes to, so this is a supersingular locus, singular locus, or more generally, basic locus of X contributes to some obvious generic Tate cycles in mid dimension. Okay, so keep this in mind, and you will see in this lecture how this what this means explicitly. So let's start with some notation. Let F be a real quadratic number field, and E over F be an imaginary quadratic CM extension. So you have this F and Q, and you choose a prime P, which is inert in F and split in E. So you have P here, which is inert here, and split into two periodic places in E. And in this lecture, I always fix an isomorphism between QP bar and the complex number. And I will denote tau 1, tau 2. The two periodic embeddings inducing the periodic place V. So here, above here, there corresponds to two periodic embeddings, tau 1 and tau 2. Here, there are tau 1 bar and tau 2 bar. Okay. And I also, so to define my Shimura variety, I need a division algebra of dimension n square plus positive involution. And also there are some conditions on the Hasse invariant for D at places which is split over F. So okay, so what is and also I need to suppose that this quadratic division algebra is split at P. So it's split into two parts, V bar. Okay. Okay, so now I take V to be D, viewed as a left D module, and consider a perfect atlating symplectic pairing on V, defined by the trace of D over Q, X delta Y star for some delta in D cross with a star of delta equals minus delta. So this defines algebraic group over Q. So this is a unitary similitude group associated to this Hermitian space. Okay, and I make an assumption that the R-valued points of this algebraic group is isomorphic to GU1 and minus 1, U n minus 1, 1 for some n at least 2. And its QP points is isomorphic to QP cross GLN EV. Okay, so of course the second assumption is a consequence of the assumption that we made on D. Now to define a Shimura variety, I need an integral. So I fix the order in OD, which is stable under star, and its localization at P is maximal and self-dual. Which? You mean the two groups are the same? No, it's not automatic. You choose delta such that. Yes, yes, of course. Okay. It's not isomorphism, you said? Oh, okay. So what I really want is, yes, the signature at infinity is 1 n minus 1 and n minus 1, 1. Okay. What? Oh, G means similitude. Yeah, it's not exactly the unitary group, but yeah, there is a similitude involved. Okay, so and self-dual under this psi localized as P, of course. And you fix also a tame level sufficiently small, open compact subgroup, open. Okay. Okay. So now you consider the functor over ZP square. So this is a degree 2 unramified extension of ZP for local Lothaриan ZP square schemes to the category of sets, which is associated to each S, the triple of A over S, iota, delta, eta, modulo isomorphism. So here, A over S is an abelian scheme of dimension 2 times n square. And iota is embedding from OD to the endomorphism ring of A, such that for each B in OE, it satisfies the cultivates determinant condition. So it's a determinant of, I denoted the variable by T, iota B on the Lie algebra of A is going to be T minus tau 1B to the N, T minus tau 1 bar B, N times N minus 1. Okay, yes. So this index corresponds to the signature of the algebraic group G at infinity. And so lambda is a prime to p polarization. Compatible with such that the starting involution induced by lambda on an endomorphism ring induced the involution star on OD. And eta is finally prime to p level structure. Okay, so by the general theory of cultivates, we know that this functor is representable by projective and smooth scheme over ZP square of dimension 2 times n minus 1. Okay, and in the following, I will denote just sh1 n minus 1 to be the special fiber of this scheme. Okay. So oh, sorry. Good. So what I'm interested in is the Tate cohomology of this Shimura variety. So you tensor with FP bar and QR bar twisted by, so for some prime number L different from P. And on this Tate cohomology group, there is action of the Heck algebra and also the Galois group of FP square. So this Heck algebra is by definition something like the double cosine of G finite at any point over K. Okay. And with K equals to Kp upper P lower P. And the lower P is just ZP square times GLN OEV. Okay. And according to the action of the Heck algebra, we have somehow a canonical decomposition. So here is going to be pi f k tensor with some Galois module that are denoted by RL pi f. So here, pi f runs through the irreducible admissible representation of G finite at any point. And I will call this part just the pi f component of the état cohomology. So let me consider, SH1 and -1 P bar QL bar. So let me consider the Galois finite part to be the union of the Galois invariants for all finite extensions of fp square. Okay, so you put here f2n -1 something. Okay, so runs through all finite extensions. So this is somehow the geometric version of the space of Tate cycles. And motivated by the conjecture, Tate conjecture. Let's say Tate of pi f. So we have an equivariant version of this. So for any pi f in the irreducible admissible representation of G finite algebraic point, this pi f component of Galois finite part is generated by the cohomology classes of algebraic cycles on the special fiber of a Shimura variety. So base change to, since we consider geometric Tate cycles, you base change everything to fp bar. Okay, this is T2. Oh, sorry. Oh, sorry. What's going on? Okay. Oh, no, not this one. Oh, yeah, great. Okay. Oh. Okay, so our main theorem is a confirmation of this equivariant version of Tate conjecture under some assumptions on pi f. So the assumptions on pi f that we need is the first one is somehow a trivial one. So you suppose that this k-invariant space of pi f is non-zero and R pi f is non-zero as well. So to guarantee the non-triviality of our result. So the second condition can be interpreted in terms of the classical GK cohomology of automorphic representations. So basically says that, okay, oh, sorry. Pi f is the finite part of an automorphic representation of G which admits Caspito base change to let's say E cross times GLN AE. Okay, So basically, the second assumption is slightly technical, but the key point is we will need a later result on the automorphic multiplicity for this pi f. And this assumption will guarantee that the automorphic multiplicity equals 1 in all inner forms of that. Okay, so and this part is not essential for our method. If you can get a better result on automorphic multiplicity for automorphic representations of G, you can probably remove this assumption. Okay, so the main theorem is the following. It's Helm, myself, and Xiao. So let pi p be the p component of pi f, and we assume that the Satake parameters of pi p are distinct modulo roots of unity then the above equivariant version of Tate is true. So actually, we can prove slightly more. That is this. So let me just write this. This Galois finite part of the pi f component is generated by the supersingular locus of, generated by the cohomology class of irreducible components of supersingular locus. So it's too long, so let's just write this of the Shimura variety. Okay. So next, I'm going to explain two things. First of all, I will explain what this means explicitly and why it appears here. And secondly, I will explain how to construct such cycles and how to analyze, or more precisely, how to analyze this supersingular locus. Okay, so to describe this condition explicitly, let's write no. In my lecture, I will not mention L function, but well, it's yes, it's essentially the same. So, what is the question again? Yes. To the order of the validation order or order of poles. Yes, but this is equivalent, I think, yeah. Yeah, over finite field. So for the Tate conjecture formulated in over Fp bar, then that means the dimension of the order of Frobenius eigen. So the sum of the multiplicity of Frobenius eigenvalue equals to roots of unity equal to the dimension of algebraic cycles, somehow like this. No semi-simplicity is used under this assumption. Okay, so you will see why. Because this assumption will exclude. So let's write pi p as pi p0 times pi v as representation of, so you say it's GQP, it's just QP star times GLN EV. Okay, so and let AVI is eigenvalue of the standard minuscule Hike operator. So this is going to P I times 1 n minus I E on this pi v k, let's say GLN OV. And denote by alpha pi v1 until alpha pi vn, the roots of the Hike polynomial rates as x to the n plus I AVI p to the I minus 1x. Okay, the roots of this. Then, the assumption on pi p is equivalent to say those pi vi are distinct modular roots of unity. Okay, so this is an explicit formulation of the condition. And secondly, let's explain why this condition appears here. This is because, according to Kotovitz, we have a very explicit description of the Galois module Ri pi f in the Grothendieck group of finite dimensional representation of the finite Galois group. So it's a certain copy of this, and there is a automorphic multiplicity involved. And then the essential part is somehow like this: chi p0 minus 1 and n minus 1 divided by 2. Okay, so here rho pi v is the L-adic representation of the finite Galois group, which sends the geometrical Frobenius of p squared to okay, sorry, such that the pi v has characteristic polynomial given by exactly this. So let's say a double star polynomial, double star. So basically, this alpha i's the Frobenius eigenvalues of this rho pi v, and here chi p0 is a one-dimensional representation. Okay, so let's just say QL bar cross. We send a Frobenius square to pi p0 p square. Yes. Okay, so and this is actually a root of unity by the theory of automorphic forms. Okay, so let's. Okay, I'm got confused. okay, this. Now a simple computation shows that the eigenvalues of Frobenius square on this wedge n minus 1 of rho pi v times rho pi v are exactly something like alpha pi v I j for I1. So minus 1 less than n. So this part comes from the wedge, and this part comes from the second factor. And this eigenvalue is of the form, which is of the form p to the n minus 1 times certain roots of unity, only when the union of this index side is exactly a 1 to n, right? And because of our assumption on the Frobenius eigenvalues, and lambda, yes. But it's still true, right? Under that assumption. Okay. So anyway, the dimension of the finite part is less than n times this cardinality of linear of Hasse principle times this automorphic multiplicity, right? Okay, so and this estimation does not use the semi-simplicity of Frobenius eigenvalues. So and now, if we can construct n series of algebraic cycles whose contribution to this RL pi f finite part is equal to this guy, then we will prove the main theorem independently of the Frobenius simplicity. Okay. So now let me explain how to construct the algebraic cycles. Construction of cycles. Basic fact that we'll need is there exists a unique, unitary similitude group called G prime for the CM extension E over F, such that G prime is isomorphic to G at every finite places, and G prime has the signature n times 0 times n and 0 n n 0 at infinity. Oh, derived group? Oh, yes. Yes, okay, derived group. Upper? Okay. Then, what do you mean? Yes, I mean it's a unitary. Okay, unitary semi-unitary group. It's not right. So then, what should be the correct formulation? But I mean, there is a unique semi-unitary group constructed in this similar way as G by just changing delta such that no. This number is not the number of groups. This is the number of non-isomorphic Hermitian space, but the associated group is the same. Yeah. This part, I'm sure it's the group is unique, but the Hermitian spaces are different. Okay. Okay, so in this way, you can have a similar zero-dimensional Shimura variety over, say, let's just consider its special fiber over fp square, zero-dimensional Shimura variety associated to G prime. Oh, okay. So not this one. Okay, it's better to use this. Now, the cycles are constructed by isogenies between the abelian varieties parametrized by sh1, n-1, and sh0, n. So you consider for each I equals to 1 equals to n, you consider the functor which is associated to locally Gaussian fp square schemes to category of sites such that S is A S iota lambda eta and B over S iota prime eta prime lambda prime and a phi. So here the first part of data is a point in the big Shimura variety, and B means a point in the smaller Shimura variety, and the phi is isogeny between B and A, compatible with OD action. OD can be level structure, and such that suppose that its kernel is contained in the P torsion, and it's compatible with polarization lambda, and most importantly, you suppose that it's induced morphism on the theorem homology, So I just use covariance theory. A over S is a local direct factor local direct factor of this, maybe of, oh, sorry, this is tau1 of rank I minus 1 times n. Okay, so this subscript tau1 means the tau1 component of the theorem homology. So because on the theorem homology there is a natural action by OE tensor with OS, right? And then there is a natural decomposition between this tau I OE to FP square, okay, and tau I bar as well. Okay, so you just take the tau1 component. And similarly, you require that the co-kernel of the tau2 component, tau2 for us is a local direct factor of rank I times n. Okay. Okay, so those are descriptions of the cycles that we constructed. Oh, sorry. Okay. The proposition is the following. First of all, each yi is representable by a projective smooth variety fp square variety of dimension n minus 1. So this is just half of the big Shimura dimension of the big Shimura variety. And secondly, there are two natural projections from yi to the two Shimura varieties, like this. And then for any z here, fp bar, its inverse limit, its inverse image, sorry. So it's I here. Inverse image. So let's say YIZ is a closed immersion for, of course, KP is sufficiently small. You have this. And each of such guys is, so this is R1. So what I'm writing. Okay, so this first projection restricts to the fiber here. Okay, sorry. Should be like this. And this guy is isomorphic to a very explicit variety in a product of Grassmanning. So it's that I call Ni. It's going to be in the product of two Grassmanning. So this means the Grassmanning classifying the I-dimensional subspace in n-dimensional vector spaces over Fp bar. And the subspace is, okay, so Fp is contained in, so here, H1 is the I-dimensional subspace in n-dimensional thing. H2 is I minus 1-dimensional thing. So, and you take a Frobenius twist of each one. We require that it contains H2, or and if you take the Frobenius twist of H2, you require that it's a local direct factor of H1 as well. Okay. And finally, if you take the union of all these cycles, then you get exactly the supersingular locus. Of the big Shimura variety. Oh, sorry. So let me give you a few examples of these varieties. First of all, when I equals to n or 1, those varieties are or isomorphic to Pn minus 1. And another example is when n equals to 3, I equals to 2. Then this guy is naturally sub-variety in two copies of P2, defined by the equation like x1 to the p y1 plus x2 to the p y2, x3 to the p y3 equals to 0. And you exchange the 0 and x and y. So here, x and y are homogeneous coordinates of the two copies of P2. Okay. And when n and I are large, then the geometry is more complicated, but anyways, explicit described. Okay. Now, our main theorem B is if you assume alpha pi v I different alpha pi v j for any I different from j, then the map that we call JL pi f, which is from H0 to SH0 and Fp bar, n copies to, so this get to H0 YIFP bar. Okay, so here you just take the pullback, and then you take, so let's write here. then you take a push forward. So basically, it's just the Gießen map or cycle class map. So you get h to n minus 1, 1. P square twisted by, and everything is Hecke equivalent under the Tate Hecke algebra. Then somehow you take the pi f as typical component of this. Okay, then this map is injective. So somehow this is our main theorem, which means the contribution of those cycles to the Tate classes is of the maximal dimensional. Okay, and this theorem B plus certain result. You mean the automorphic multiplicity? Yes. So actually, what we need is the two automorphic multiplicity are the same. So theorem B plus this pi f automorphic multiplicity in G equals to G prime. Okay, plus this fact, then will imply theorem A. All we need is this equality. Yeah.
But that means that also that means that a posteriori this inequality is
A plus 0.
the inequality in Fox
Uh-huh.
must be equality.
Yes. 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 Exactly. So, because we already have that maximal dimension, so and the whole proof does not need the Frobenius semi-simplicity. Yeah. Okay. Yes, and I think this result is maybe well due to White or maybe and also others. Okay, but I find a reference in White's paper in the form that I stated. Okay, for the proof of theorem B. So to prove theorem B, I will compose this JLF pi f with so this is n minus 1 pi f with another morphism. So here you first pull back using the first projection, so you get minus 1 for I equals to 1 to n. And then you use the, so since each yi is projective smooth of dimension n minus 1, actually equidimensional of dimension n minus 1, and using trace map, you will see that this guy is naturally isomorphic to n copies of that. So basically, you consider this composition, which is the intersection matrix of those cycles, actually. So you first make Gießen and then pull back, make the restriction to each component, and take the trace. So So what we do is we can compute explicitly this matrix on pi f. So let me give you a few examples. For example, when n equals 2, then this pi f is of the form minus 2p minus 2p, here AV1, and here AV1, and so let's just say SV inverse. Here SV equals AVN. So let's put a special name. And AVI records that it's the eigenvalue associated to the Hike operator like this, I minus I. And so if you take the determinant of this guy, it's going to be 4p squared minus AV1 squared, so SV minus 1. And then you use the relation between the alpha i's with this coefficients, you will get immediately it's equal to minus p squared alpha pi v1 minus alpha pi v2 square alpha pi v1 alpha pi v2 in the denominator. Okay, so and now suppose if n equals to 3, the intersection matrix is of the form, well, it's 3p squared minus 2p AV1 AV2 minus 2p AV1 3p squared AV2 SV inverse AV1 and times SV inverse and in the middle is more complicated. Okay, so again, if you take the determinant of the whole matrix, then you will get alpha pi vi minus alpha pi vj, I different from j square. In the denominator is alpha pi v1 I. Okay, it's just the product or the Frobenius eigenvalues and the square. So okay, let's just write n minus 1. And here is up to sign. There is a factor here, p to the 8. Okay, so anyway, once you compute this intersection matrix and its determinant, you find that as long as the Frobenius eigenvalues are distinct, then the whole intersection matrix is non-degenerate, so its contribution is maximal. Oh, okay. Oh, yeah, this is the this is the most technical part of the whole proof. So basically, so you look at one component yiz, and you're trying to find all the yijz prime such that the intersection is non-zero, is non-empty, and you will find that immediately that by a calculation in terms of Diodoli module, you will find that this happens exactly when z prime is in a certain Hike orbit. Okay, so Hike orbit of z. So I mean, so it's not so precise. I mean, the Hike operator associated to this is something like p square, p in the middle, and 1 something. Oh, not p 1 in the middle, and p minus 1 something. Right. Anyway, there is a Hike operator, spherical Hike operator, such that this happens exactly when z prime lies in the Hike operator. And another important thing is the intersection. This intersection is also the same kind of variety as yiz. So which means it's also a subvariety, closed subvariety contained in the product of Grossmaning, but with a smaller index, probably. And so basically, you need to compute the intersection number of this. And you have to evaluate a certain so-called access bundle on the intersection. Then you will get a number. Yeah. So this is basically the strategy, but there are many explicit computations involved. Okay, so I think I stop here.